Okay, 7.2, solving similar triangles. In today's lesson, we're going to be solving mostly for side lengths in a pair of similar triangles, and sometimes a few angles in similar triangles. So remember this. Similar triangles have equal corresponding angles. And it's important that we say the word corresponding, because if we just said that they have equal angles, that wouldn't necessarily be correct. It'd be a little bit misleading. I think I would know what you mean, but it's important that we use the proper terminology. Similar triangles also, right, they have equal corresponding side length ratios, which just tells us that, hey, the two triangles are proportionate to one another. Like there's some sort of scale factor involved. It's like this triangle A and B, right? We got one that is 3 times as big, yeah, or one that's 3 times as small. So here's a warm-up. It says proportion says that two ratios or fractions are equal. And being a grade 10 student, you know that 1/3 is in fact equal to 2/6. You might know that because this right here, this fraction of 2/6, can be reduced, right? And it gets reduced to 1/3. So 1 out of a total of 3 is proportionate to 2 out of a total of 6. So this is here. So 1 out of 3 is equal to 2 out of 6. The ratios are the exact same, right? So yes, these things are in proportion, right? Like 1 to 3 is the same as 2 to 6, because we could just reduce this one over here, right? Divide that by 2, divide that by 2. And we get the same as the original here. Great. We've probably seen that before. Now, down here, this is some good stuff. You may have seen this before. It says when things are in proportion, then their relative sizes are the same. It wants us to solve each of these equations. So this is kind of similar to solving equations involving fractions, but if you look closely, they're all proportions. They're all proportionate. It's saying that something divided by 5 is the same thing as 4 divided by 10. Now, some of us might notice that 10 is twice as big as 5. Yeah? So if we were going this away, if we wanted to go from 10 to 5, we would divide by 2, right? And that means that because these things are proportionate, we'd have to do the same thing on the top here, right? We'd have to divide this also by 2, and x, the value of x, 4 divided by 2 would just give us an answer of 2. But that's because that's a pretty, for some of us, might be an obvious answer. Now, it's important that we come up with a strategy that can work for all different types of proportions, because if you look where we're headed, I mean, that might be a little obvious, but not too obvious. This one here is a little bit nasty, and this one over here is also a little bit nasty. So it's important that we come up with a method that'll work for any proportion. Now, some of us might use the strategy of cross multiplication, which would work here, but I personally don't use that. What I like to do, and I would like you to all get in the habit of, is, well, solving for x like we do when we're just solving equations. And if you notice, we currently have x over 5 equals 4 over 10. So if we wanted to get rid of the dividing by 5 here on our x variable, we would have to multiply by 5. And whatever we do on one side, we must do the same thing to the other side. What happens is the multiplying 5 and the dividing 5 cancel each other out, and we just get x on the left-hand side. And on the right-hand side, what you can do is there's a couple things. Well, first, you could just use a calculator, and I think that's your best bet. But another thing is, remember that 5, right, the whole number 5 as a fraction is 5 over 1. So when you're multiplying two fractions by each other, right? You do numerator to numerator, so 4 times 5 is 20, and then 10 times 1 is 10, and we get x equals, well, 20 divided by 10 is an answer of 2. Now, if that whole, multiplying fractions thing just seems too far in the past, that's totally fine. What you could also do is just go to your calculator, put it in brackets, 4 divided by 10, close the bracket, and then multiply it by 5, and it'll spit out the answer of 2, just like that. Maybe we'll try that method in the next example. So let's look at part B. Part B, we have 7 over 12 equal sign x over 48. So we want to solve for x. And some of you might notice the proportion here, right? 48 and 12. Right? Yeah, you might see something going on there. You might notice a relationship there. Now, in order to get rid of the divide by 48, we are going to have to multiply by 48. And what we do to one side, we must also do to the other side. Yeah? So 7 divided by 12 in my calculator gives me a nasty, humongous decimal that I'm just going to leave in my calculator. And I'm going to times that whole nasty decimal by 48. And I get 28 exactly, yeah, equals, well, 48, 48, they cancel each other out. And we just have x. I'm going to put little boxes around my answers here. Okay, this next one, kind of nasty, right? It's not like the first two. In the first two examples, x was a numerator. And for some of us, we might have noticed some sort of relationship or some sort of scale factor or proportion going on between the two fractions. But in this case here, it's kind of nasty. And there is a way around this. It's a really nice way. What I'm going to do is, well, since we're used to having the x on top, we're just going to put it there. We're going to invert this fraction. And because we did that on one side, we have to do it on the other side as well. So we're going to have x over 1.5 equals 10 over 2. See how we just flipped both of the fractions. Now, we're going to do exactly what we did in the first two. Multiply, and we're going to get rid of the dividing by 1.5 by multiplying each side by 1.5. Sorry about this penmanship. And multiplying 1.5 cancels with dividing 1.5. Get x on the left-hand side, equal sign. I go to my calculator, I do 10 divided by 2, and that is 5, and I times that by 1.5, and we should get an answer of 7.5. And the last one, very similar to, oh, that was a straight line. Look at that. That's impressive. I'm going to save this one. Okay, 7.5 for that one. Great. This last example, similar idea. X is on the denominator. We don't want that, so we are going to flip. Well, we have to flip both. If we're going to flip one, we got to do it for both. So we're going to have here x divided by 8, and over here it'll be 15 over 10. And if we want to solve for x, we're going to have to get rid of the divide by 8, and we do that by multiplying by 8. And whatever we do to one side, we must do to the other. Yeah. On the right-hand side, the divide by 8, multiplying 8 cancel out. We're just left with x. And on the left-hand side, I'm going to go to my calculator, do 15 divided by 10, press equals, and I see that 1.5. I'm going to take that 1.5, times it by 8, and we should get an answer of 12. Okay, folks, at this point, if solving proportions is not the craziest thing in the world for you, then we're going to be in good shape for solving similar triangles. Okay, let's look at our first example. So example 1. Find missing sides and missing angle measures. So if you notice, it says here, given triangle ABC is similar to triangle DEF, find the measure of angle C and the length of DE to the nearest decimal. Now, it's important to note that they deliberately told us that these triangles are, in fact, similar. So we don't have to necessarily prove that the triangles are similar because the question already told us that. It said, hey, look, they are similar, I promise. Now, help me find angle C and side length DE. That's what they've said. So first, find the measure of angle C. So let's put maybe a little header here and say, okay, solving for angle C. Here we go. And angle C is only in triangle ABC. Of course, it's this one right here. So we're not really looking at triangle DEF just yet. Or maybe we are. If you notice, we have angle B, which is 121, and angle A, which is 28. So a third angle in any triangle, right? We know all triangles have to add up to 180 degrees, and I think you know what to do here. We are simply going to say, okay, 180 equals 121 degrees plus 28 degrees plus whatever angle C is. And now what we can do is just go ahead and solve for angle C. And we're going to do that by isolating angle C, moving the 121 and the 28 over to the left-hand side. So now, when we do that, we have 180 minus 121 minus 28 equals C. And, where is it? Well, maybe it's not there. So we can say, we go to our calculator, 180 minus 121 minus 28. 31 degrees is equal to angle C. So I'm going to go to my diagram here and write in 30. Well, I'm going to try my best here to write in 31. Yeah. Okay. Now, that being said, maybe we can do a little bit of an aside here. Notice that angle C and angle F are equal, meaning they're corresponding angles. Yeah? Angle B is 121, and angle B corresponds to angle E, so that would be 121. And lastly, angle A corresponds to angle D, so D would be 28 degrees, just like that. So if we wanted to solve for all of them, we can surely. The question didn't ask that, I know. The next part of this question was find the length of DE to the nearest decimal place, meaning, okay, how long is side length DE to one decimal place? So we are going to solve for DE. We already know that the triangles are similar to one another, so we know that the corresponding side length ratios are equal. So we're going to go ahead and set them up. I'm going to use triangle ABC as all my numerators, and then triangle DEF, the smaller one, as all the denominators. So when I set up my ratios, I'm going to have to pick and choose here my corresponding side length ratios. So let's use red. So AB corresponds with DE, right? So maybe we can even write that down. AB corresponds with DE. Next, we could say BC corresponds with EF, right? And all these ratios will be equal to one another. And lastly, the bottom here, CA corresponds with FD, just like that. So now that we've set up our corresponding side length ratios, yeah, I got a little colorful over here. What we're going to do next is now try our best to fill in the blank. So for example, let's have a look at AB. AB can be represented as just 12.1 units, right? DE, there's nothing there. In fact, we're solving for DE. We are solving for this one right here. So maybe we could even highlight it and say, oh yeah, this is the one we want. How about BC? BC we don't know, and EF we don't know, so they can kind of just stay as is. And lastly, CA is 20.1 and FD is 16.1, like that. Now, if we want to solve for DE, we're certainly going to need to grab this ratio here if we're solving for DE, and then we can't really use BCEF because nothing's really there. But what we are going to use here is 20.1 over 16.1 because there's actually information there. So BCEF, that ratio doesn't really help us at all. So let's just grab these two here. We have 12.1 over DE, which, DE we're solving for. And we're going to say that this is proportionate to 20.1 over 16.1. And here we go, right? Just like we did on the first page. We're going to flip probably both of these fractions, right? We're going to have DE on top, and if we flip the one side, we're going to have to flip the other side as well. So we should get DE over 12.1, and on the other side here, we should get 16.1 over 20.1. Notice how we just flipped them. Now, at this point, just like we did on that first page, we're going to multiply each side by this denominator, right? Because we're trying to solve for DE, so we got to get rid of the dividing by 12.1. We do that by multiplying each side by 12.1. They both cancel like that, and we're just left with DE. We go to our calculator and I type in 16.1 divided by 20.1, and we get a nasty decimal, but keep that decimal in your calculator, and it times that by 12.1, and we should get 9.692, and so on. But it just wanted to the nearest decimal place, so we can round that to just 9.7 units. So there you have it. DE is 9.7 units. Okay. Example 1 in the books. Example 2, a little bit more tricky. So I put some helpful steps here because these steps are really good because it's going to help us solve kind of anything. And maybe I'll use them, number 1, 2, 3, as kind of a guide here. So let's read this question. It says, find the length of side length FG. And we know this is a side length because it's 2 letters. So side length FG to 1 decimal place. So the first step in the helpful steps says state the triangles. So if we have a look at this diagram, there's two triangles. There's FGJ and HIJ. Right? You see those two triangles there? So maybe we could go ahead and write them down. Triangle, that'll be step number 1, we'll put there. Triangle FGJ and triangle HIJ. Now, what it doesn't tell us in this question is that the triangles are similar. So that leads us to part 2. We have to prove that these two triangles are in fact similar. So how are we going to do that? Well, how about this? Notice that angle G and angle H are both 90. They're equal to one another. So let's go ahead and write that. Angle G is equal to angle H. And the reason is that they're both 90 degrees. And that's given. That's given to us as a gift. Sorry about the penmanship. And angle, now the textbook might like to say FJG, but really I'm just talking about, what have I done? Clicking stuff, it's not working. There it is. Angle J is equal to angle J, and we know that because they are both opposite angles. So we can go ahead and say opposite angles. Wow. I'm going to go ahead and start typing here. So now we can say, therefore, triangle FGJ FGJ is similar to HIJ. And the reason for that would be, let me slide over here, angle-angle similarity. That's what we're dealing with here. Angle-angle similarity helped us prove that these two triangles, right, triangle FGJ and triangle HIJ, are in fact similar. Now that we know that they are similar triangles, right, we proved that they're similar, we know that the side length ratios will be equal to one another. So let's go ahead and set up our corresponding side length ratios. So I like to go with a highlighter, and I'm like, okay, well, I do know that starting from the 90 going towards J, right, HJ would correspond starting from the 90 going to the HJ corresponds with GJ. And then we got opposite of the 90 degree, this long side here. FJ corresponds with IJ. And lastly, maybe we can use, I don't know, blue. FG on the very outside corresponds with HI on the very outside, like that. And I use these colors to kind of just help me out when I'm setting these up. So this will be part 3, setting up the corresponding side length ratios. Here we go. FG corresponds with HI. Those are the blue ones. GJ corresponds with HJ. Those are the, where are we? Green ones. And JF corresponds with JI, which is the yellow ones. So these are the corresponding side length ratios. We got it. Lovely. And then step 4, what we're going to do is we're going to complete these ratios and then solve for the unknown variable. So let's go ahead and fill in some of the blanks here. So we can go ahead, we know FG, we don't really know what it is actually. Actually, that's the one we're solving for, right? Don't forget that. So I'm going to highlight that one for us. GJ and HJ, there's nothing really there. And JF is 18.9, JI is 6.3. Great, this is step 4 here. Good. Now again, be very, very cautious. You know, I'm going to put a couple stars here. I'm going to actually do this one in red. And we got to remember, like, keep it consistent with the triangles. So notice that I had triangle FGJ on top. Yeah. I'm going to put a little ratio here. And then triangle HIJ was consistently the denominator. And that is a good way to not start flipping and flopping some of these triangles. Because once once you lose sight of, you know, these corresponding side lengths, once they're out of order here, it'll lead you down the wrong path. So we're going to grab this ratio, of course. We're going to grab the completed ratio, of course. And we don't need this one at all because it doesn't really give us anything. So we can go ahead and grab these two ratios. And look at this. We're going to use these ratios to solve for side length FG. It's dividing by 4.3, so we're going to get rid of that divide by 4.3 by multiplying by 4.3. We got to do that to each side here. Great. On the left side, they cancel. And finally, we get into our calculator, FG equals 12.9 units about, so that's rounded to 1 decimal place. Okay, and that would be step 4, and that's it. Great. Not bad, right? A lot of work is shown. There's lots of marks up for grabs here, so it's super important that we show our steps. And we got to remember here, you know, keep this consistent. Holy, keep this consistent. I didn't think it was that bad writing with the pen. I don't know what happened here. We're writing with my mouse. Okay, in the last example, it says you're in the diagram, line segment DE, so this Y here, DE, the one that's 36 centimeters, is parallel to side length AC, this one down here, and it's already drawn in there. You can kind of see it. Maybe I'll exaggerate the lines a little bit more just to not to forget that these two lines are in fact parallel to one another. And I got the helpful steps here again. So first, we're going to state the two triangles that we're dealing with. Yeah. Actually, maybe read the question. We're solving for side length AC. Yeah. Some people might even want to put an X here. Yeah, like X or something like that. I like to leave it just AC. We're solving for AC. So what are the two triangles we're working with here? So notice that there's a big one, big triangle, ABC, the big one there like that. Then you got a littler one in there, the DBE, that little triangle in there. So those are our two triangles, triangle ABC and triangle DBE. Now we have to prove that these two triangles are in fact similar to one another. Now we haven't, the question hasn't told us that these two triangles are similar, so we got to make sure that we go ahead and prove similarity exists. Now right off the hop here, I noticed that angle B is in both of the names of the triangle, right? So that kind of tells me a little bit that that angle, especially in this scenario here, is common. It's a common angle. It's a shared angle between the two. So I can say angle B is equal to angle B, and we could say that it's a common angle. Okay. And then, what do we have here? We have parallel lines. So you might notice some patterns. I see an F pattern like that, which tells me that angle A is equal to angle D. So maybe we can go ahead and write that. Angle A is equal to angle D. Some of us might have, no, that's because of the F pattern, which we know as corresponding angles. Okay, therefore, we can say triangle ABC is similar to triangle DBE because of angle-angle similarity. Great. And that is step 2. We proved similarity exists between the two triangles, which again tells us, hey, there is a lot of relationships with the side length ratios. So that'll be our next bit. Set up the side length ratios. So AB corresponds to DB. Yeah? It's like AB is there, DB, it'd be right on top. Yeah? BC corresponds with BE. And lastly, CA corresponds with ED. Again, very important that we keep, notice how I kept triangle ABC as the numerators every single time and triangle DBE as the denominators every single time. It's very important that we do that. We do not want to end up flip-flopping. So this is part 1. Yes, part 2 was prove similarity. Part 3 was set up the corresponding side length ratios. And step 4 is to use the complete ratio and the one with the variable to solve. So AB over DB. Oh, see, now this is kind of a tricky one, because AB is going to be the 12 that's here plus the 48. So that gives us a total of 60 centimeters for the length of AB. And then DB clearly is just 48. Yeah. BC we don't really know, and BE we don't really know. And lastly, CA corresponds with ED, and ED was 36. Now let's not forget, AC is the same as CA. It's just, it's tomato, tomato. So we are solving for side length CA or AC. What we're going to do is we're going to grab the completed ratio, and we're also going to grab the one that has the variable and something else in it. Good. We're going to set them equal to one another. And you could either cross multiply here or just solve for CA by multiplying each side by that denominator, which is 36. Cancel, cancel. I go over here, I go right to my calculator, and I do 60 divided by 48, and it gives me 1.25, and I times that by 36, and we get 45 exactly. So AC, or CA, whatever you want to call it, is 45 centimeters in length. Good, that's step 4. Okay, folks, that's solving similar triangles. We have homework here on page 380, number 6, 7, 8, 11, and 12.